start from the place where we left last time, and we will solve to get a closed form solution. So the PL, the call loss probability is, I think that's where I left. Probability of being in state sigma, arrival rate, probability of call loss conditioned on sigma, summation over all sigmas actually. So that's where we started. We have identified individual components. I think for P of sigma, that's what we were doing, and we could get to a solution which was, I think I have not proven that it was MC. That was probability of being in state X, and correspondingly probability of being in state Y was that's what we had done. Okay. This I had got from Angst distribution. So very quickly, just recalling that, what we did was, being in state X was zero to M. We are taking case where M is smaller than N actually. Okay. So this can only go till N. You can only have N. You can only have M occupancy, not N. So that was the probability of being in state X, and correspondingly it is true for state Y also. X, you make it I actually, that's better, so it will not confuse. Okay. And what I did, I think, if you recall quickly, I think I did very fast because it was in the end of the class. Now this is a complete binomial, so I can always write this thing as 1 plus lambda by mu raised power m. Okay, this is coming from complete binomial, and then I moved it, we just modified this thing. It is mu plus lambda raised power m, mu raised power m. Okay. And what I did is, I said, okay, let's put lambda plus mu as A. The reason for doing this was, if I divide by actually, if I take mu out, this will be n lambda, so this will be 1 over lambda plus 1 over mu. This value will be equal to this. So on time scale, if this is the first call arrives, the call remains there, call actually goes away, call is cleared, the next call arrives. So this duration is approximately 1 over mu, and this duration is approximately 1 over lambda. So this technically gives nothing but the fractional utilization, and we also define this as a load in Erlangs. Okay, Erlang is the name of a gentleman, and then since he had contribution to switching, so to respect him, it's given as Erlang. So now how much Erlang offloads? So for one telephone line, the fractional utilization cannot be more than 1. If you have 1000 input ports, and if you have 0.9 fractional utilization per line, so it will be 900 Erlangs load on the whole switch. Okay, that's the way it will be defined. we solve it further actually. No, because call cannot arrive. See, when the line is busy, the call is on hold, no call can arrive during this period. And it is not between two, because it's a special kind of process. You take any particular time instant, it need not be that call should have been arrived that time. And after how much time the call will arrive? The average time will always be 1 by lambda. That's the beauty of this particular distribution. Because call cannot arrive here, call will only arrive after this. So this should not be included in the arrival rate, because that time line is busy, occupied, call is already there. So 1 by lambda corresponds to this entity. If you converse, put all 1 by mu is equal to 0, then it will be exactly whatever is the Poisson process which we have learned. But that's why it is done this way. Because telephony, it is peculiarly in this fashion, because it is a circuit switch scenario. So now solving, I need to just convert everything to A, and this will give me this thing actually. I think this is a step where I missed out. So I require and of course 1 minus of A is 1 minus of lambda plus mu. Okay, so I will just do that conversion. So from here, you know what has to be done. So mu m minus x. So I have to take out mu plus lambda, m minus x. So here mu minus mu plus lambda, x will be left because this sum has to be equal to this. Mu m minus x I have already taken, lambda raised power x will be here. So take this and take this, and you will end up in getting this. Okay. So Px and Py both are known to me. I have already determined what is going to be lambda xy. This also we had determined. We also had determined this is a middle stage switch. Okay. So K is the number of switches in the middle stage. Okay. With that we had also found this. So all things are there. I have to now put it in that summation and then solve for it actually. So I will do this. So remember, it's a dual summation. Sorry, this has to be.
First in the previous class we had done for n, small n, number of things. So this lambda xy was sigma delta n minus 6 into n minus 1. And similarly on the top equation also, sir, k was replaced by n. Last class it was n.
Okay. That's, yeah, you are right, because R will be equal to n. I am using a different notation, that's. But anyway, now I will not use this so that there is no confusion. I do it correctly. Okay. So it will be n minus x n minus y summation over xy. Xy is the delta or gamma. Okay, what which is used? Sorry, I think there I have used gamma last time. Just check in the previous thing. I have used delta, so I will keep on. This anyway will cancel. I am not bothered about it. This anyway will cancel. Well, that's why I have taken a constant for which I don't know the value. So I have put in your lambda sigma has been put. Now let's put P of sigma, which is multiplication of these two. X and y both are independent. So I have done this Px Py. Now conditional probability x factorial y factorial divided by x plus y minus n factorial. So numerator part has been done. Okay. What I will do is I will try to solve in this equation, and I will go slow so that, because you have to rewrite the equation, I can erase the board and do it. And this will be I think this cannot be n, this has to be k, because the reason for this is this, I think the way I have taken, because k is greater than n, that is why this gets converted to ncy. Only n maximum connections can take place at any point of time. Okay. Input line is m and this is n. So in that case I have to use m here actually in that case. Look at the expression, this should be m. So I think to be consistent I will just change, wherever n is there I will just put, this should be again m. I can observe the inconsistency otherwise. This is then n, it will be fine. So this is actually n and this we are using m, because I have my derivations with nk actually. Anywhere is there anything else wrong? No. So this I have to change. This is fine. So kindly verify that everything is correct. Okay. So it's as per this notation now.
Lambda sigma was in terms of n. So this would be n.
Lambda sigma, no, this cannot be n. Incoming line, how many are free? N, small n is greater than m.
So number of maximum calls will be n only.
M. Number of maximum calls can be n, even if n is larger. You cannot have more than m calls. Only m of these A links can be occupied. No? Well, that's what I derived. I think there is same confusion, nk thing. In my lecture notes, I think it is written as nk on the website. So that's where the mistake is. But anyway, forget that website. I have to be consistent with whatever I am doing in the class. And you should be capable of modifying all these symbols whenever required. Okay. Because I also remember it with nk. But then since I have been doing mn, so I will be doing mn, not an issue. So I have to actually now, I cannot take m minus x and m minus y out of this xy summation. You have to understand this. But I can take delta very clearly without any issue. This delta can be taken out. This delta will be cancelled. Fine. Expand these mcx and mcy. Do the same thing here. It's nothing but a step by step evolution now. Okay. So I can cancel this and I will become minus 1. This will become minus 1. I can write this m factorial as similarly this factorial can be written as okay. I can take these m square out. I can do the same thing on the numerator side. So I will end up in m minus 1, m minus 1, minus 1. This is fine. N factorial is independent of x and y, so this can be taken out. Okay. So m square cancels. I can remove this. Now this particular thing can be written as, if you look at this expression, this is nothing but m minus 1 cx m minus 1 minus x. So there is one extra 1 minus a which will be there. Okay. Similarly for this I can also write 1 minus a m minus 1 c of y so I can very well replace this whole thing, and 1 minus a square can be taken out. X and y both are independent here. Okay. And there was earlier one extra term that will actually become 0, obviously, which you can verify. So one term has been now reduced. These two are independent. So it is nothing but complete binomial. And I can replace, I can actually simply write this thing as summation over x and this as summation over y. That is possible. This thing is nothing but 1 raised power m minus 1, which is equal to 1. So this whole denominator is gone. Perfect. You have only 1 minus a square. Okay. Now let's look at the top stuff, what we can do. I have to use some trick here now. M minus 1 factorial square actually can be taken out. Okay, so this is no more required. And now I will split into two summations. One is x, other one is over y. Okay, I will do it over x later. First over y and second one over x. So anything which is having y, I will keep it on this side. This x factorial cancels with this y factorial cancels with this. This is what you have. So I am just going to rewrite it actually. Let me rewrite first. So that's what you are going to have. I can now multiply and divide. Just a minute, I will do something. I have to do that. No? I am just splitting that, sorry. Okay. So this one I will keep here. Summation. These two terms actually will come here after this summation. So this is what is the summation for y. Okay, that is summation for x. And I will then multiply and divide by something. So what is sum of these two? That has to be independent of y. That's the only condition. It should not be function of y. So one is having plus y, other one is having minus y. So it will actually cancel if I add. So I can multiply by that whatever is the sum factorial of that. I can put that in numerator as well as in denominator. That is the simplest way of doing it. So it will be m. Just add these two. Plus x minus n minus 1. You can put in your numerator. Same thing I have to put, and this I can take out because it is independent of y. Yeah. So this one is. Now this 1 minus a square, I need not even keep this line. 1 minus a square, I can just put it in here. And this thing, this is summation over y. Now what are the valid values of y that you have to figure out? So valid values of y will be, they will be ranging from, so first thing is this actually should become 0, and secondly this should become 0. That's how you will actually get the range. Okay. So y will be actually varying, one extreme it will be x plus y, sorry, x minus n. N minus y, you make it 0. N minus x. Now this is the condition when x plus y is equal to n, just when the blocking starts. If x plus y is less than n, blocking cannot happen. Okay. This is just when the blocking starts. This is the first case. So the y will actually range from this value. For rest everything, this will go to 0 anyway. You cannot have summation over those terms. Other terms has to be removed. Even if all other possible values of y is there is 0. I am only going to sum up only this range when blocking happens. Only those terms are there. So I am not estimating when blocking is not possible. Those cases I am not considering in my term. So that's why when that condition x plus y is actually smaller than n happens, those cases are not coming in. If that situation is satisfied for your switch, this will give you value 0 actually. So we have taken care of. Earlier case in least approximation, we were not isolating those conditions. We are not removing them. Here in the summation term itself, when the blocking is happening, I am removing those. Because those becomes invalid values, otherwise I cannot sum it up. If I take y is equal to going from 0 to n, it is not possible because terms will be invalid in that case. I cannot build up a closed form solution. So while building up closed form solution, I am actually removing or excluding those terms. Okay. This is actually usually is not evident, so I am explicitly stating this. So the next range will be coming from here. Y will be m minus 1, obvious, because there is one line which is free for which you are trying to, on which the call is coming. You are not looking at blocked state, you are looking at when a call comes, whether it will get through or not get through. So in worst case, it will have m minus 1 states. Okay, you cannot have higher than this, it is not possible. So this is the range over which this summation will be done. Then only I will get a closed form solution, otherwise I cannot get a closed form solution. So because the moment I take this summation, because this is nothing but a binomial now, I can now convert it into a binomial. I have to put something, this a raised power y is there, x I can take inside now. I can call it a x plus y. There is minus n here, okay. So I can put, just a minute. This is minus 1. So I have only 1 left here. I will also even remove this, and this will be converting it to minus 1. I will put, I require minus n here, I will put a raised power n here. Okay. So still everything is in balance. Now this is value matches to this, and m minus of this, or basically this value comes here. This is now complete binomial. This is the range, which is also the valid range when the blocking happens. I am removing all other terms, so I can do the summation, and I will end up in getting. So range concept is very important, because usually unless you appreciate this, you will not be able to figure out that why you are getting the correct probability of call blocking. Correct you are getting because I am not taking in this summation other terms which corresponds to the cases where blocking does not happen. Those have been removed. Okay. So this now you can solve. So y variable is not there on this side. So what will be the value? A plus 1 minus a raised power m plus x minus n minus 1, that should be the value, p plus q raised power n in binomial. This is nothing but 1 raised power something. This whole thing is unity. Once it is unity, I can simply remove this. Excellent, we have got this. One step closer to further solution. Now, if I add m minus x minus 1, this m plus x minus n minus 1, right? If I add these two, again I will get a range of x by keeping this as 0 and then this as 0. Okay. So sum of these two is how much? 2 of m, x will cancel, minus 2 minus n. So I have to just take the factorial of this and multiply and divide. Done? This anyway can go out, so I am not bothered. I am only bothered about now this particular piece. Again you have to look at the range. So what terms you are excluding? What all values, possible values of x you are excluding is important here. So now one possible range will be m minus x minus 1 is equal to 0 you put, so x will be m minus 1, which is valid because that is the maximum which you can get. But what is the minimum value of x? So x will be n minus 1 n plus 1. Yeah, minus m. That is a minimum value of x which is there. I remember in earlier case it was based on y was ranging, y's range was depending on x actually. When you are computing range for y, it was depending on x. So whatever, but x has to be minimum chosen as, any one of them can be least actually depending on what is the value of n. If n plus 1 is on this side, remember this, these many number of ports and these ports. Physical interface, these number of ports are double the, this n plus 1 is greater than or equal to double the value of m, then x will be, this value will be, usually it will be lower actually. This will only be higher if it is more than double the value of m.
Highest value x can take will be that we take m, that all calls are coming on input port.
Only m minus 1 calls are there. Na? Worst case scenario.
Yes, so n minus m minus 1 is equal to n plus 1.
You are right, this will be. Because if you actually go out of this range, again the blocking will not be possible, blocking will not happen. Now why this is happening? If n minus m minus 1 is this, if my x is less than that, on the other side m minus 1 can be occupied and I am having value less than this. There is always possibility whatever combination you take, it will be always non-blocking. Only if this difference is fully covered. Remember, I have done a case. In this case, can blocking happen? Blocking cannot happen. Blocking has to happen only if whatever is the leftover is covered by this minimum. Minimum value has to be this, and that's what I am writing. N minus m minus 1. N minus m minus 1 is total subtracted. That is this value. So this value minimum has to be equal to this, and maximum it can go to m minus 1 anyway. So this value has to be lower because x cannot be higher than m minus 1. So this is a lower range, lower value, and this is higher. Okay. And the case which I am taking when n minus m minus 1 becomes equal to m minus 1, that is a strictly non-blocking switch in that case. Probability of call loss will be 0. Okay, that will immediately, so the summation, all terms will go out actually in that case. You will not be including any term in that case. So again, it means I am only taking the values in this range, then it will be a complete binomial, otherwise it will not be. So I can now solve it. So I have m minus 1 factorial square n factorial 2m minus n minus 2 and this is nothing but a plus 1 minus a whole raised power 2m minus 2 minus n, complete binomial. A cancels with this, it is 1. So no, I have made a mistake. What mistake I have made? I have done something, but it is incorrect. You have to have these terms which corresponds to these. I don't have term for a which corresponds to this here. So, I cannot simply write a plus 1 minus a and then say equal to this. No, that is incorrect. This a raised power n actually should come out. This is independent of x. This is not varying. So, I have to take it out. Okay. I have to put some other term here. So, I will put 1 m minus x minus n minus 1. That is the way of doing it actually. So, once I do it, it is 1 plus 1 minus a yeah, a raised power n, because we had minus n was used here earlier in the previous step. In the summation where we did summation over y, we have moved it inside. A raised power minus n was required, so we created a raised power n here. A raised power x actually was moved inside there, so that you can have a raised power x plus y minus n. Okay. So, this is what is the closed form expression for probability of call loss. So, I will write it as m minus 1 factorial a raised power n 2 minus a 2 m minus 1 minus n n factorial 2 m minus 1 minus n. And remember, this is nothing but call blocking probability, and we have estimated that call blocking probability will be a function of n minus 1. If n minus 1 is replaced by n, this will end up in this is a switch being in block, this is a time congestion, this is a call congestion. This we had already computed earlier for a composite switch. So, there is an alternative proof, because this is a call blocking probability. You can also do when the switch will be in the blocking state, that estimation. That is known as Jacobius approach for call congestion estimation in the same 3-stage network. And he will actually get the result where P of, this is P of L, P of B will be this is M, Jacobius got this expression. And can you observe these two and these two? The same relationship still holds. Same relationship still holds. So, there is an alternative approach through Jacobius. The name of the gentleman who did this alternative derivation. So, that gives you the call blocking probability. Okay. So, now next we have to go into the all kind of theorems, so that we can formally figure out that why a switch is strictly non-blocking, or why a switch is rearrangeably non-blocking, and why a switch is wide sense non-blocking. And can we reduce their cross point complexity further? I want to minimize on cross point complexity as far as possible. So far what we have figured out is O and 3/2 for a strictly non-blocking switch. Can I make still better than that? Okay. Yes, we can do still better than that. We can get O n log 2n, log 2n's power 2.58. But how this 2.58 comes is interesting. This can be derived, it is not a heuristic number. We will do that derivation. But before that, when I go through now formal proofs and formal theorems regarding this, you have to understand the concept of Paul's matrix. So again, it is a name of gentleman in switching theory, and this is a very, very handy tool in giving all kind of formal proofs, theorems, lemmas, everything comes from here. Okay. So I have sufficient time to actually explain what is this Paul's matrix, what is the meaning of this. 2 by 2 it's simple to do, but if multi-stage number of ports can be arbitrary, any kind of thing, and then you have to do a formal proof, you require this. So you will have 3-stage switches, and I have lot of middle stage ones. Important thing is that if I take any other input and output pair switch, the path between these switches is not blocked by the paths which are connected between these two switches. Okay, that is extremely important. I can set a path between this and this independently of this and this. If a path between this and this is being set up, that may lead to blocking of a path being set up between these two. So at least either input or output switch has to be common for the blocking to happen, or for the interference in setting up of the switch. So in fact, I need not look into this, that is very generic, I think you should be able to appreciate that. And I will give now some values, say A and B. This can be numbers are also nothing but symbols to represent, they are formed from a set, but we have built up our own arithmetic on that, or an algebra by which we can define the complete number system. So it does not matter for me, it can be any arbitrary symbols, that is good enough. Okay, because the algebra here is pretty simple. I can write this as the middle stage switch is F, G, H, I, J, whatever you want to put. And what we will do is, we can always create a matrix, that is why it is known as Paul's matrix. Okay. And if for example this between A and B, if I want to set up a connection, so all the rows corresponds to the input stage switches. Okay. So these are input stage switches. And what should be these columns? Output switches, obviously. See, remember, the science is very symmetric in nature. So if you understand symmetry and beauty of it, it is going to be very, very simple. Anything which is ugly, probably it is incorrect. That is a thumb rule. And you will have here output stage switches. So I will just explain something and then leave it for you, and we will go ahead with this particular thing later on. If a switch A is here, switch B is here, so number of switches, number of columns, number of switches, number of columns. A and B I can set up path through many of them. So if I have set up a path through F, there is already a path happening. So I will put entry F in this cell, which is common. But this cell need not have one entry, it can have multiple entries also. If I am using G, H, I, J also to set up path between these two, I will put those entries also, F, G, H, I, J. But F and G has already been used for A and B, but A I am using to connect to some I, to some other, say some Z. So for the Z column, in that cell, I will put this I. Okay. So that is what is known as Paul's matrix. Only thing now you have to understand is, okay, I am actually giving it as an assignment, you try to think about it. You can even look into the notes, that is your choice, but I will appreciate if you try to think on your own and come with the conditions. and later on verify with the notes, or anyway I will tell that. Okay. What are the conditions of validity of this particular pulse matrix? If I give you a pulse matrix, can you check whether it's a valid pulse matrix or not? My conditions like how many times entry can come in a column, can it repeat? Will I have only, F can come only once in the row, or F can come only once in the column? Okay. Can F come at 2 or 3 places? How many entries can be there at most? So try to think about all those conditions. You have actually understood quite a bit already. Only thing you have to just convert it into now this, and amazingly you need not visualize the switch after this. You can just work with this pulse matrix blindly after that. Okay.